Hi folks, welcome back to the videos on 12.7 spherical and cylindrical coordinates. And in this video, we're going to take a look at how we convert whole equations to a different form, okay? So let's take a look at example 4, all right? We're going to look at 4 different equations, and all of these equations are already in rectangular form, and we're going to convert them to our cylindrical form. But before we convert to our cylindrical form, let's think about identifying what each of these three-dimensional surfaces actually looks like, okay? All right, so let's get started. We'll take a look at letter A. So we've got z equals 2 minus x squared minus y squared. Now, this doesn't necessarily look like one of the equations on the quadric surfaces graphic organizer. But I want to do a little bit of algebra here and see if we can't kind of suss out what it is that we're looking for. Okay. So what we're going to do, we've got z equals 2 minus, and I'm going to go ahead and factor out a minus sign from the x squared and the y squared. Okay. And so when I do that, I really get z equals 2 minus the quantity x squared plus y squared. And if we remember from our graphic organizer, if we have a z equals x squared plus y squared, that shape is an elliptic paraboloid. Elliptic paraboloid. Okay? But this 2 minus in the front really just means we have an elliptic paraboloid, like the bowl. It's turned upside down, and that's the minus sign. And then the 2 means that we've now moved up that elliptic paraboloid 2 units. Okay. So it's an elliptic paraboloid. It is upside down. And the vertex is at 0, 0, 2. Okay. So when we're thinking about knowing our shapes, it's important to know like the regular equations, but also basically like how graph transformations work for our surfaces, okay? So we've got this z equals 2 minus the quantity x squared plus y squared. We've identified the shape. And now let's think about how we use all of our conversions from that graphic organizer to help us convert from rectangular to cylindrical. And one thing we might notice is that x squared plus y squared is another way of saying r squared. All right. And so if we make that substitution, we'll get z equals 2 minus r squared. Okay. So the r squared replaced the x squared plus y squared. And now we have a function that is in our cylindrical coordinates. Okay. Now, if we start to think ahead, like why is it important to kind of be able to switch from rectangular to cylindrical coordinates? We might notice that like just by switching coordinates, we now, instead of having two inputs, we really have the one input. And if we think about taking integrals or derivatives, it's often easier if we have a single variable, right? So that might be one sort of motivation for moving coordinate systems. I think in general, also, as we're integrating or taking a derivative, 2 minus r squared or 2 minus r squared might be easier to work with, okay? All right, let's take a look at part B. So part B looks kind of similar, but it's z equals the square root of x squared plus y squared. Okay. Now, if I want to compare this to what I have on that quadric surfaces graphic organizer, let's go ahead and square both sides. So when I square the left-hand side, I get z squared. But when I square the right-hand side, that gets rid of my square root, and I just get z squared equals x squared plus y squared. Now this, I hope we remember from our quadric surfaces, is not an elliptic paraboloid, but it is a cone, and it has a vertex at the origin, and it is opening up along the z axis. Okay? So we might think about it like our shape is going to look something kind of like this. Okay. Now that we've identified the shape, let's go ahead and convert to our cylindrical form. Now this one, again, the moment I see x squared plus y squared, I really want to say, well, let's just throw an r squared in to replace that, okay? So we'll end up with z squared equals r squared. We take the square root, and because we don't define radii to be negative or an r value to be negative, we really just got z equals r as the cylindrical equation for a cone, okay? Now, again, sort of thinking forward to if we have to take an integral or if we have to take a derivative, I could integrate this, I could take a derivative, but z equals r is a way easier function to work with. And so that's why having the ability to change coordinate systems might make our lives easier when we actually get to the calculus. All right, let's take a look at this third one. We're picking on some classic quadratic surfaces here. We've got x squared plus y squared plus z squared equals 4. And this is something we saw very early on in the semester in like the general form x squared plus y squared plus z squared equals our radius squared. And anytime we had that, that was really our way of defining a sphere, okay? So let's go ahead and write 4 as 2 squared. And now I know that this is a sphere with the center at 0, 0, 0, and a radius of 2. Okay? And if we're thinking about like practicing to sketch for some of the work we're going to do in the later chapters, a sphere might look something like this, with that center there and a radius equal to 2, okay? But let's now go ahead and convert this to its cylindrical form, because maybe we can save ourselves a little bit of a setup here, okay? We've got our classic x squared plus y squared, so let's pop an r squared in for that, plus z squared equals 4. And this would be an absolutely fine way to define the sphere in our cylindrical coordinate system. So r squared plus z squared equals 4. All right, we got one last one over here. X squared plus y squared equals 1. Let's think about what this shape is in R3, okay? So we're in R3 for all of these. X squared plus y squared equals 1 is not the unit circle in R3, but rather it is a cylinder, right? So there's no z component, so we're taking the circle and we're stretching it in the z direction. So we have a cylinder with a central axis of the z-axis, right? And a radius of 1. And so if we imagine what this looks like, we get something kind of like this, opening along the z-axis, and we've got a radius of 1, okay? We know it's a radius, that's a good connection, but we also want to make sure we know that we can convert this into our cylindrical coordinates. So x squared plus y squared equals 1. I hope we're sensing a trend. We've seen x squared plus y squared in like every single one of these questions, right? This really gives us r squared equals 1. All right, well, if r squared equals 1, r technically equals positive or negative 1, but again, r equals 1 versus r equals negative 1, we choose the positive one and we get r equals 1 as our cylindrical equation for a cylinder, okay? And would we rather integrate or take a derivative of x squared plus y squared equals 1 or r equals 1? I think that something like this might just be a lot easier to work with, okay? So we'll stop this video here. In our next video, we're going to take a look at converting from rectangular coordinates to spherical coordinates.